Assalamualaikum and hello everyone. I am Nurul Natasha binti Khamdani. My matrix number is 502202252235. And this is my project for Mathematics for Engineer and MB 10103. I am from Bachelor of Mechanical Engineering with Honours. Today I show you how a small pieces of math, just a little curve, can explain real world pressure, prevent explosion and keep engine running safely. Let's start simple. A partial derivative tells us how one thing changes while everything else stays still. In gas system, we use it to measure how pressure changes when temperature increase but volume stay fixed. This is written as partial P over partial T, and this is a little formula. It's used in engineering, physics and even rocket science. So, why does this matters? Because in real system like gas tank, engine or rocket chamber, pressure build when it get hot. If we don't know how fast it's built, things can go wrong fast. Partial P over partial T give us the ability to predict that pressure before it become dangerous. This help engineer maintain safe operation under the heat. Here the core formula, which is PV equals to nRT. This relate pressure, volume, temperature and gas amount. Let's rearrange the formula, which P equals to nRT over V. Now, we focus on partial P over partial T, the rate of pressure change when the heat increase, assuming volume stay the same. So here what we are solving. If temperature increase in a sealed gas system, how quickly do the pressure rise? That's what partial P over partial T tell us, and knowing this will help engineer control pressure and avoid system failure. We start with the gas law. P equals to nRT over V. Now take the partial derivative of pressure with respect to temperature, which is partial P over partial T equals to nR over V. This formula shows that pressure increase linearly with temperature depending on volume. Let's see in action, which is N equals to 1 mole, R equals to 8.314, V equals to 0.01 meter cube. So now we plug in the value, which is 1 times 8.314 over 0.01. The answer is 831.4 Pascal per Kelvin. That means for every 1 Kelvin temperature rise, pressure increased by 831.4 Pascal. That's like 88 balloon of pressure in just 1 degree. Now, let's go through a real example of how we apply partial derivative in gas law. Imagine we have sealed gas container with a fixed volume of 0.02 meter cubic and contains 1.5 mole of the ideal gas. Our goal is to find partial derivative of pressure with respect to temperature, written as the partial P over partial T. This tells us how pressure changes as temperature increases while keeping volume constant. We start from the ideal gas law, which is P equals to nRT over V. Then we take the partial derivative of pressure with respect to temperature, which is the volume stay constant. Partial P over partial T equals to nR over V. Now, we plug in the value, which is N equal to 1.5 moles and R is 8.314 joules per mole Kelvin. And V is 0.02 cubic meters. So, the calculation become like this. Partial P over partial T equals to nR over V. So now we just plug in the number into the formula, which is 1.5 moles times with the R, which is 8.314 over V, which is 0.02. So the answer is 623.55 Pascal per Kelvin, written as PA per K. So that means for every 1 Kelvin increase in temperature, the pressure increased by 623.55 Pascal. Wow. That's a big jump, and this is exactly why engineers use this math to make sure pressure doesn't reach dangerous level in gas system. So here a real life example to help visualize a partial derivative. Imagine a sealed gas tank under the sun. The volume stay constant, but as temperature increase, the pressure rises. The partial derivative partial P over partial T tell us how fast the pressure increase with temperature when volume doesn't change. This helps us to understand the predict pressure build up in closed system. So, in the end, this simple formula, partial P over partial T, help us predict and control pressure in system, gas cylinder, car engine, air conditioner, and also a rocket. It helps engineer control pressure before it's become a problem, whether it's cooling system or space travel. Partial derivatives are behind the scene, keeping these things safe. Partial P over partial T is more than a formula. It's a powerful tool for engineer helping us understand how gas react under heat. This knowledge turns math into action and safely into science. That brings me to the end of my presentation. I hope you now have a clearer understanding of partial derivative, especially partial P over partial T, are applied in a gas system. It may look like a small formula, but it plays a big role in engineering, helping us predict pressure change and prevent system failure. Thank you so much for your time and attention. If you enjoyed this video, please don't forget to like, comment something nice, and maybe share it with your friend. Your support means so much to me. Thank you for watching.